In this example, we're going to use Stokes' theorem, the surface integral, to calculate the flux of the curl of the force field, the vector force field F, across the surface S in the direction of the outward unit normal vector N. So my vector field is y minus zi plus z minus xj plus x plus zk. And my surface S is in a parametrized form, the vector r in terms of r and theta, so polar. We have r cosine theta I, r sine theta j, and 9 minus r squared k. My r values are between 0 and 3, and my theta values are between 0 and 2 pi. Now for Stokes' theorem, we need the double integral across the surface of del cross f dotted with that outward unit normal vector n with respect to surface area, and that will be calculated with dr d theta. So first we need del cross f. We have f here. Let's go ahead and calculate del cross f. So working through this, what we'll get after we've set this up with I, our partials, and then each of our components from f, which once we start working looks like this. So I've got to find these three mini determinants. And after we work those partial derivatives through there, I have negative I, 1 minus negative 1, that's plus, so we'll get 2. So we have minus 2j, and then we've got plus negative 2k. So that represents this del cross f. Now what we need is n. We need our outward unit normal vector. So I'm going to clean up my screen here so we see what we're looking at better. So for our second step, when we need to calculate n, n is going to be r partial r cross r partial theta divided by that magnitude of that cross product. So the cross product of those partials will be normal, and then in order for it to be a unit vector, we need to divide it by the magnitude. So let's find each of these partial derivatives. So r partial r, that is going to give me cosine theta I plus sine theta j plus, or we could say minus, negative 2rk. And our partial theta, that's going to be negative r sine theta I plus r cosine theta j, and we will have 0 k values there. So that cross product, r sub r cross r sub theta, it's going to be I, j, k, cosine theta, sine theta, negative 2r, negative r sine theta, r cosine theta, and 0. And we should be proficient at calculating this at this point, so I'll just write that out. And pause if you need to check your work or to check my work. But 2r squared cosine theta I plus 2r squared sine theta j plus rk. That represents r sub r cross r sub 0. So I'm going to clean my screen up. I'm going to pull this back up to the top of the problem. So we've calculated del cross f, and we need to dot that with n. But let's look at what that looks like. We can save ourselves a little bit of work here. Remember, I said that the the outward unit normal vector n is going to be r sub r cross r sub theta divided by its magnitude, right? It's the magnitude of that vector. Now let's look further in depth at this integrand that we're dealing with. So my integrand is going to be del cross f dotted with n, and then we've got d sigma. Now we're dealing with surface area for a parametrized surface. So what this means is I have del cross f. My unit normal vector is going to be r sub r cross r sub theta divided by its magnitude. And then what is d sigma going to be? Well, we will have r sub r cross r sub theta dr d theta. Since this is a surface integral and we are dealing with a parametrized surface, we need to go back to our surface integral formula, and we're going to include that as part of our differential. Right now, what we notice is that this is a scalar value, and I left my dot product notation out here, but when I dot product the two of these, this scalar is just going to multiply and add through. So I can save myself a little bit of effort, and these guys will cancel. I don't need to actually calculate the magnitude of this vector. I mean, I could, it's not very much work. The magnitude of r sub r cross r sub theta, and you can check it if you want, is going to be r square root of 4r squared plus 1. So essentially all I'm doing is taking that dot product and dividing through by this scalar value of magnitude, and then I would multiply by it later. Okay, they cancel. So back to our flux curl integrand. So now that we know that we can simplify it, we don't actually need to calculate that magnitude. So before we actually set up our integral, let's just simplify this integrand a bit. So really all we need is del cross f dotted with r sub r cross r sub theta. So we need to calculate this dot product here, right? So again, cleaning up. So setting up my integrand to be del cross f dotted with r sub r cross r sub theta, I've got -1, -2, -2, and 2r squared cosine theta, 2r squared sine theta, r. So what this dot product looks like is we've got -2r squared cosine theta minus 4r squared sine theta minus 2r. This represents our integrand. So setting this up then, my double integral across my surface, again, del cross f dotted with n d sigma, and that's going to equal the integral. Now, we're dealing with, this is my integrand, this is in terms of r and theta. Remember, theta was between 0 and 2 pi, r was between 0 and 3, that was given. So we've got 0 and 2 pi, 0 and 3. My integrand I just found, -2r squared cosine theta minus 4r squared sine theta minus 2r dr d theta. And we don't need that extra r factor in here in this situation because we're not converting. We're just dealing in polar coordinates. So it was given this way. And now that we've moved past all of that, now we just have a very easy integration. So first let's integrate with respect to r. Got 0 to 2 pi. That's going to be negative 2/3 r cubed cosine theta minus 4/3 r cubed sine theta minus 2, I'm sorry, that'll just be minus r squared. We need to evaluate that from 3 to 0 and then integrate again with respect to theta. So keep in mind these are r values. We're plugging 3 and 0 in for r. 3 cubed is 27 times 2 divided by 3. We got negative 18. 3 cubed, again 27, times 4 divided by 3. We have negative 36. And 3 squared gives us 9. Plugging in 0, those will all go away. So now integrating with respect to theta, I have negative 18. The integral of cosine is sine theta, plus 36. The integral of sine is negative cosine, which changes that sign, and then minus 9 theta. We'll evaluate between theta equals 2 pi and 0. And I know often we discount the 0, but we cannot in this situation, so I'll plug in 2 pi first. I've got negative 18 sine of 2 pi, that will go to 0, plus 36 cosine of 2 pi. It's going to be 36 times 1, we'll get 36, minus 9 times 2 pi, so minus 18 pi. And plugging in 0, we'll get minus all of this. So we've got negative 18 sine of 0, which is 0, all of that, plus 36 cosine of 0, which is 1, or we've got plus 36, and then minus 9 times 0, which is 0. So 36 minus 18 pi minus 36, we get negative 18 pi. And so this is the value we get when we used Stokes' theorem. We used this surface integral to calculate the flux of the curl of the field F, the vector field, across the surface S in the direction of the outward unit normal vector. Cool. We're all done. That's it for now. Email with questions. Ta-ta.